Hello, so welcome to this video. So in this video we'll be exploring where most of the mass of things around us actually comes from. Now you might think it comes from interactions between fundamental particles and Higgs field. And indeed, the mass of the individual fundamental particles does come from interactions with the Higgs field. However, when these particles, so in particular kind of quarks, combine together to make composite particles, and we call these composite particles hadrons, and hadrons is called for heavy ones. They're much heavier than the quarks that make them up, and in fact the mass of these hadrons is bigger than the individual mass of the fundamental quarks which make up these hadrons. So if most of the mass of composite particles doesn't come from the mass of the fundamental particles which make the composite thing up, then where does most of the mass of composite particles, and therefore most of the mass of you and I and the stars and the galaxies and planets actually come from? That is what we'll be exploring in this video. So if we're going to talk about where most of the mass that makes up you and me, or planets and stars, or many things in the universe comes from, we need to talk about atoms, because we're made up of atoms, or molecules which contain atoms, and in the sun we have in its interior a lot of ions, so essentially charged versions of atoms, and therefore, if we're going to understand where most of the mass of things come from, we have to look into the atom and see, where the mass is concentrated within the atom. And so the idea of an atom, and actually particles being made up of indivisible atoms, actually goes all the way back to ancient Greece. Now at that time, they obviously had no way of seeing atoms, and therefore this was very much an area of metaphysics. Individuals like Aristotle believed that things were made up of atoms, and according to Aristotle's picture, was things being made up of atoms, all atoms were, identical. However, we had differences in matter based on the arrangement of those atoms. Now it's worth saying Aristotle's views on the composition of matter may have evolved over time, but he was at one point at least a supporter of the idea of a particle, atomic, if you like, model of nature, but the atoms were identical. It was just their different arrangements that gave matter different properties. And that's not too far off what we have today, in some ways, with the idea of isomers, so molecules which have the same number of each element of atoms in, but have those atoms arranged differently, can lead to isomers having different properties. Mostly different physical properties, but there are subtleties in terms of the chemistry of different isomers as well. And therefore, we know today that, yes, the arrangement of atoms matter, but today we're aware that, an atom of one element is different from the atom of another element. And to consider different elements, we need to look inside of atoms, into the nucleus. So Rutherford was one of the first people to provide evidence that an atom actually has a positively charged nucleus, and he did this by firing alpha particles at essentially gold foil and seeing how the atoms in the gold foil interacted with the alpha particles, and particularly the thing he ended up his experiment ended up indicating was that an atom contained a dense positively charged nucleus which could repel the positively charged alpha particles. Now, at the time of when Rutherford did his experiment, they didn't really know what an alpha particle was, but they did know it was positively charged, so they could deduce that this nucleus had positive charge. And by looking at the fact that very few of the alpha particles were actually deflected by significant angles, one could tell that this positive charge in the atom was concentrated to a very, very small region. And this region is the nucleus of the atom. And, every atom has a different nucleus, because it turns out to be the positively charged particles within the nucleus that determines what element the atom is of. So, for example, in hydrogen nuclei have one proton, but helium nuclei have two protons. Oxygen nuclei have 8 protons, carbon nuclei have 6 protons, so on and so forth. And it's the number of protons that determines the element. Now, actually, most of the chemistry of elements come from the electrons, not the protons in the nucleus. And the electrons are the things that orbit the nucleus. However, to make atoms neutral, and given that the positively charged particles in the nucleus of the protons have the same charge, have the same size of charge, magnitude of charge as the electrons, an atom needs as many protons as it does electrons. So once you determine the number of protons of an atom, that determines the element, that also dictates the number of electrons in the atom, and therefore governs the chemistry of that element. So we have this very, very dense nucleus, and actually most of the mass of an atom comes from the nucleus. So we might go, we've already answered our question of where most of the mass comes from. It comes from the nucleus and the particles which make up the nucleus, so our protons and our neutrons. However, protons and neutrons, it turns out, are not fundamental particles, they are composite particles. They're made of quarks, particularly they're examples of baryons, so particles made up of 3 quarks. And these quarks are the up and down quarks. And so if we look inside, in our diagram here at the bottom, we have 2 up quarks and a down quark, so we have a proton. You might go, if most of the mass of the atom comes from the protons and neutrons, and the protons and neutrons are made up of up and down quarks, then most of the mass of the atom ultimately will come from the masses of the up and down quarks. However, that turns out not to be the case, because if we look at the total mass of quarks, for example, in a proton, and it's a similar value for the total mass of quarks in a neutron, so we can extend this argument very much to neutrons. and get similar answers. But for protons, the total mass of the quarks that make up the proton is about 10 megaelectron volts per the speed of light squared. If you're not familiar with megaelectron volts per the speed of light squared, it's a common unit to mass within particle physics, and that is to say completely uncommon and barely used at all outside of particle physics. But in this video we're looking at where the mass of things come from. We're trying to get to the fundamental particles, so we're using particle physics units, and particle physicists love inventing units and names of particles. But anyway, the total mass of the quarks in a proton is about 10. The total mass of the proton, however, turns out to be, nearly 400, if we go round. So nearly 400 megaelectron volts per the speed of light squared. And if we compare 10 to our 398, so about 400, you can convince yourself that the mass of, only about 1% of the mass of the proton actually comes from the mass of the individual quarks which make that proton up. So in other words, only about 1% of the mass of matter, because matter is primarily, most of the mass of matter is found within the nucleus of atoms. Electrons have barely any mass. So most of the mass of kind of atoms actually doesn't come from the particles that make those atoms up. It doesn't come from our, up and down quarks. And that might be a little surprising, because it's like, well, where does most of the mass then of matter come from, if not from the constituent particles that make up matter? It seems bizarre, but the key to solving the mystery is looking at our diagram of our quarks inside our proton a little more carefully, because we don't only have quarks, we have forces connecting them, which I've modelled as springs. And it's actually the force, so the interaction between quarks, that gives a proton, and similarly a neutron, and therefore, an atom as a whole, most of its mass. So most of the mass of matter comes from the interaction between quarks. And we'll explore this a little bit more on the next part of the video, before doing a calculation to look at how strong this interaction is and what effect that actually has on our protons and neutrons. So we said that most of the mass of a nucleon, so a proton or a neutron, doesn't actually come from the constituent quarks that make it up. So where does it come from? Well, although it doesn't come from the rest mass of the individual quarks themselves, it comes from energy associated with interactions between the quarks. And this energy essentially gives the proton or neutron a lot more mass than can be accounted for if we just considered the rest mass of the quarks alone. And the idea that energy can correspond to mass, or if an object has a lot of energy, it will act like it has a lot of mass, is embodied in Einstein's equation E = mc². It essentially goes a certain amount of energy E is equivalent to the amount of mass m, where E and m are related by E equals mc squared. Now c is the speed of light, which is quite a big number. So, typically where we're not giving objects much energy, like kinetic energy, E over c squared is going to be quite small, or at least a lot smaller than the object's Rass mass, so the mass it would have if it was stationary, and therefore an object behaves to a good approximation like it has its normal Rass mass when in motion. And this is why if you pass a mug of tea to someone, you don't have to worry about relativistic effects on the mass of the mug of tea as you're moving the mug, because the kind of kinetic energy you're giving the mug only gives the mug an additional tiny amount of mass compared to its Rass mass. However, within our kind of nucleon, the interaction between our quarks is governed by a very, very strong force, actually called the strong force, and so the potential energy associated with the interaction is huge. And actually, therefore, corresponds to an amount of mass which is far bigger than the Rass mass of the quarks alone. So it's the strong force, or really the potential energy within the strong force, which is actually the origin of most of the mass within a proton and neutron, and therefore most of the mass within kind of everyday objects. And also even most of the mass within mesons, so particles made up of two quarks. Again, it comes from interactions between the quarks. Now, we can model this strong force by thinking of the quarks as being attached by springs. And the reason we can do that is because the strong force will try to keep the quarks at a happy distance, just like a spring will. Because if we've got two masses connected to a spring and we push the masses apart and then release the masses, the spring will cause the masses to go back closer together. The spring will contract back to its natural length. So, the strong force is acting like a spring, and equally, if the quarks get too close together, then the strong force will push them apart. So again, the quarks return to their happy length. And this kind of restoring nature of the strong force causes actually the quarks to oscillate, or these bonds to oscillate. And that actually can cause changing size of the protons and neutrons. And so for the rest of the video, what we're going to do is calculate firstly how strong these bonds are, using the analogy of thinking about the bonds as springs, and then we're going to calculate how quickly the oscillations of the quarks occur, and therefore how rapidly the size of the protons and neutrons fluctuate. But the strong force is really cool because it determines really the ideal distance between the quarks, and therefore the density of the protons and neutrons, and therefore the density of nuclear matter as a whole, and also therefore the density of neutron stars, so as applications in astrophysics. And it also, crucially for this video, the strong force gives a hadron, so a baryon or a meson, most of its actual mass. Or in particular the kind of potential energy associated with the strong force. And that potential energy is huge because the strong force is very, very strong, allowing for the effective mass associated with the potential energy to be a lot bigger than the individual Rass masses of the quarks within the hadron. So we want to be able to essentially calculate how strong the bond is that is holding our quarks together within a nucleon, and that is going to correspond to essentially the stiffness, if you like, of the spring, if we're using a spring as the analogy of our strong force or strong interaction. And because the strong force is acting like a restoring force and the quarks aren't getting very far away from each other, and also, a proton doesn't naturally collapse into a black hole, so, the quarks aren't getting ridiculously close together. Because of these things, we can kind of think of the spring as being stretched as the quarks move, but not being stretched so much that the spring permanently deforms. Or in other words, we're considering the strong force to have a constant strength, approximately, as our quarks are oscillating about these kind of interquark bonds, if we want to use more chemistry language. And therefore we can use Hooke's law to model our spring, if you like, or to model these interquark bonds. And Hooke's law relates the energy stored in the bond to the strength of the bond through the stiffness constant, and also the extension, so how much the quarks are moving by. And, well, Hooke's law, when applied to the energy stored in the spring, looks like this anyway. You can write Hooke's law in terms of the force itself, so not the potential energy of the force, but the force itself, and the extension of the spring. But for our purposes, because, we've got information about the amount of extra effective mass the bonds are going to have to correspond to, we can get information about the energy within the bonds. So it makes sense to use this form of Hooke's law. If we were going to, use the amount of force itself, we would need other information. So this equation relates the energy within one interquark bond, so E1 with the strength of the bond given by the symbol K, and the extension, so how much our kind of bond is being stretched or compressed by as our quarks oscillate, and the extension is given the symbol E. And if we're going to calculate the kind of like total elastic potential energy in our springs, if we're using a spring analogy, or the total potential energy associated with the strong force between our quarks, what we can do is use the fact that the effective mass that this energy produces is going to have to equal the difference between the mass of the nucleon as a whole and the mass of the individual quarks that make up the nucleon. And then, once we've got that effective mass, we multiply it by the speed of light, so we go from MeV per c squared to MeV to get the energy in all these interquark bonds. So I've got symbol 3 here below the E to emphasise that this is the energy in kind of, in total, so in all our 3 bonds. And to get the average energy in a single bond, we'll have to divide it by 3, but first of all, we'll have to, if we want to use the average energy E1 in an interquark bond, we'll have to convert energies into joules. And we can convert into joules, before we find the average or after we find the average, it doesn't really matter. So if we're converting before we find the average, we multiply our energy in megaelectron volts by 10 to the 6 times 1.6 times 10 to the minus 19 to convert it into joules. And this gives us that the total energy in all our 3 bonds combined is 1.48 times 10 to the minus 10 joules. And then if we divide by 3 to find the average energy within an interquark bond, we get 4.93 times 10 to the minus 11 joules. Now that might sound like a really small amount of energy, but the kind of extension of our springs, so how far our quarks are allowed to get from each other at best, is really, really tiny. So even though the energy is tiny, because the extension is tiny, we actually end up with a large stiffness constant, okay, which is measuring how strong this interquark bond is. But to get K as well as E1, so the average energy within a interquark bond, we need small e, so we need the extension. And here I'm going to use a bit of an approximation. I'm going to go, well, because proton and neutron remains roughly same kind of size, I'm going to take at maximum the extension to be comparable with the kind of average size of a proton or neutron. And to get the average size, we can look at the diameter. And when we've got our quarks distributed within our proton or neutron in 3D space, there's lots of ways they can be arranged. So it's quite hard to find the average distance between the quarks. And therefore to get a kind of estimate for the extension of the springs, if you like, or how far the quarks can kind of deviate from each other. But to make it simpler, and we try to find approximations, so it's a fair thing to do. To simplify our model, let's imagine that the proton isn't a three-dimensional object. Let's imagine it's a one-dimensional object. And if it's one-dimensional, the quarks are essentially just all arranged along a single line. And the size of that line will correspond to the diameter of the proton, which is about 1.7 femtometers. And if all the quarks are in a line, then the average distance between the quarks is going to be, the length of that line divided by 2. So we can imagine, for example, at one end of the line we have one quark, the other end we have another quark, and in the middle we have our third quark. So the average distance between our quarks is the entire line divided in 2. And that will give us about 0.85 femtometers. But if we're going to use the extension in our equation, so within our version of Hooke's law, to find how strong the interquark forces or bonds are, we need to convert extension into meters. So to do that, we times it by 10 to the minus 15, and we get 8.5 times 10 to the minus 16 meters. And if we substitute the value for this extension and our kind of potential energy within a single interquark bond, we get the strength of the bonds is I think truly whopping 1.36 times 10 to the 20 newtons per meter. And that means for every meter we would for every meter we want to pull our quarks apart, we would have to apply a force of 1.36 times 10 to the 20 newtons. So that's pretty huge. That's a force you would have to apply against the strong force to push them apart by a meter. Now, it's worth saying that really this is the kind of stiffness constant when the quarks are bound together within a hadron. If we in reality try to pull the quarks apart and keep going long before they are separated by a meter, what will happen is so much energy will build up within this interquark bond that the energy is enough to be converted into actually, bunches of quarks and will form, if you like, a shower of hadrons. Essentially, so much energy builds up that almost the bond snaps, but that released energy is converted into the mass of other particles. So these bonds are incredibly strong, and hence the strong force. And you might think that, okay, if the bonds are really, really strong, then the particles are going to oscillate really, really quickly because the restoring force is going to be huge. And indeed, they do oscillate really quickly. In the last bit of the video, we're going to explore exactly how quickly that is. So we've now got a number describing how strong the interquark bonds are, and it's really, really, really strong. And if we're looking at the mass of the kind of quarks being held together, we can link that with the strength of this interquark bond to get the frequency at which this spring, if you like, needs to oscillate to give the necessary potential energy within our interquark bond. And when we're going to be looking at finding the angular frequency and then the time period of oscillation, we are going to be approximating a little again, but this is about finding a good approximation. And that's a really useful skill in physics because ultimately in physics we are always approximating. Even if we're using exact values, we're using models which are inevitably making simplifications, and we do this all the time in physics. So we're always really dealing with approximations. So if we're looking at the mass on our spring or connected to our interquark bond, it gets a little complicated because in a proton and a neutron, the up and down quarks have different masses. Additionally, because their masses are so small and the bond strength is so great, these quarks can move at relativistic speeds, meaning that their actually mass is variable. Additionally, if we look at our kind of quark model, each quark is connected to the two other quarks. So we really have a coupled system, and a fairly complicated coupled system. So to work out the correct mass we should be associating with a single bond, to get the actual answer is somewhat mathematically involved. But for an approximation, we can just take it to be the mass of the two quarks connected by a single bond, and we can take the mass of the quarks to be, the kind of average typical mass of the quarks. And if we're looking at two up quarks in a proton, generally on average, together they would have a mass of about 5 megaelectronvolts for the speed of light squared, or if we're converting that into kilograms, that's about 8.89 times 10 to the minus 30 kilograms. So I'm going to take that to be the mass that is connected to our spring. And then we can use equations from simple harmonic motion. So essentially, motion where the spring constant or the bond strength remains a constant. And we get for the angular frequency that the angular frequency of the oscillation of the quarks, and therefore the oscillation of the changing size of the nucleon, is about 3.91 times 10 to the 24 radians per second. And then we can use equations from circular motion to convert that into the time period of the oscillation. And so we get a time period of 1.6 times 10 to the minus 24 seconds. And that means a proton will kind of contract and expand. It will undergo one full oscillation every 1.6 times 10 to the minus 24 seconds. So protons and neutrons oscillate in size incredibly quickly, and it's because they oscillate in size so quickly we can, for practical purposes, which involve interactions over much larger time scales, consider the size of a proton or neutron to remain roughly fixed. Now it is worth saying that in this video, as I say, I'm treating the potential energy of the strong interaction classically, and I'm also talking about size of an object in a very classical manner. I'm not taking into account properly quantum mechanics. Well, I'm not really taking into account quantum mechanics at all, apart from postulating that these quarks make up protons and neutrons, and the evidence for that is related to quantum mechanics. So because of that, when I say the size of a proton or neutron doesn't change, you have to take that with a grain of salt. Because if we calculate the wave function of a neutron or proton, that may well change, giving a changing average size to the neutron or proton. But what we've done is model neutrons and protons classically, and that gives us a good kind of like average values. I mean, that's what classical physics is really good at, giving us average values. So averaged out of all kind of quantum interactions, we tend to get numbers similar to these. So, it's just something to bear in mind. But I think what we've done is pretty cool. We've essentially deduced, really just by using Hooke's law and thinking in detail about the composition of protons and neutrons, the rate at which the size of protons and neutrons change. And we've also discussed the origin and mass of a proton and neutron, so I think we've covered some pretty cool kind of material here. If you enjoyed this video, I would recommend keeping an eye out for other videos on the channel, because this channel covers a wide variety of things, and we have kind of other videos on kind of particle physics stuff as well. But that's everything for this video, and in this channel I will try to do a mixture of individual videos like these and also playlists. So at the moment working on one on general relativity, and also got a last few videos on the special relativity playlist planned. So fair amount of stuff happening, but I hope you've enjoyed the video, got something out of it, and I'm wishing you a very wonderful week ahead, and keep exploring the wonderful world of physics, and I hope to see you for some more wonders soon.